All right, so we're going to take a look at 9.2 part 2, okay, getting into graphing a little bit on the calculator. And we're going to go over how to convert between all the different systems we've used. We've already done like taking something that's parametric and making it a function. It's called eliminating the parameter. We've done the reverse of that by letting x equal t and then substituting t in your original formula. So we've changed between functions and parametric. We're going to do parametric to polar and polar to parametric today. Okay. So remember, in polar, your points are written as r comma theta. So let's graph something like this. R equals 2. So what this means is you can pick basically any theta you want as long as r is 2. So could somebody give me, let's do it in degrees, give me a point that would satisfy this equation.
229.37.
2, we'll just say 29 degrees. Okay, so let's graph that. 2, 29 degrees. All right, what's another point that would satisfy that?
2, and then
2 what?
Pi over 6.
Let's do it in degrees.
45. No, 46.
All right, so 2,
Well, no, 45 is amazing.
45.
46.
Okay, what's another one? Yeah?
2 and 67.3257.
Okay, so there's that. Another one.
2 negative 200.
2 negative 200. Okay, so 2, and then negative 200, well, brings me halfway around, and then I'd have to go 20 more. So I'd be over there.
2 negative 55.
So 2 negative 55, that would put me about right there. And the idea is if you keep graphing all these points, all of them, for every possible angle, what shape are you going to get?
Circle.
You're going to get a circle.
So would you just draw a circle?
Yep. So the idea in polar is a circular equation is very simple. Anytime you have r equals a number, you get a circle that has a radius of that number. Right. And you can plot more points, but they're all going to end up making a circle. Hey, questions on that? All right. Now, let's try something a little different. This is kind of like saying, you have y equals a number when you do a function, and then you do x equals a number. Well, this is like the other one now. You let r equal a number. Now you're letting the other part of your coordinate equal a number. So now, the points for this one have to have an angle of 2 radians. And if you're not, just to get an idea of what 2 radians is, let's multiply it by 180 and divide it by pi. So that's about 114 degrees. Okay, just to remember that. That's what the angle is. So what would be a point, and we'll do it in radians, but for graphing it's easier to think of it in degrees. What would be a point that's on that graph?
2.456.
2.4 comma what?
The angle, too.
The angle. So 2.4 comma 2. So let's go out 2.4, and then we're going to go to 114 degrees, which puts me 90 and a little bit past that.
It's going to make a line.
What's another point? Yeah?
798,232.
That's off my grid. Next.
4.
4 comma 2.
You don't have to.
4,
So we're just putting
2.
2 and
1.
Okay. 1. Okay, so 1, 2. Another one.
0.
0, 2. Okay.
1.5.
1.52. Okay.
-3.
So we need negatives too, because we're not getting the whole picture yet. -3, 2. So now you're going to go 3 to the left, and you're going to go a little bit more than 90 degrees.
It's going to make a diagonal line.
So now we're getting the whole picture.
It's called a slanted line. I'm sorry.
So if you let theta equal 2, you get a slanted line, depending on the angle. It could have a positive or negative slope. And lines that go through the origin are not that bad to draw. Questions on that one? All right, now, let's say, how do we graph a line normally? Like, not as a, like the system you're used to using. What's the standard equation?
Y equals MX plus B.
So y equals mx plus b. Now, yesterday we had a formula for x and y to convert them into polar. What was our formula for x?
R cosine theta.
R cosine theta. And what was the formula for y?
R sine theta.
R sine theta. So let's take that, put it in there. Take that, put it in there. And remember, when you do something in polar, you have to get r by itself if you want to graph it on the calculator. That's how you have to do it. So once we make these substitutions, what we're basically doing is converting the equation of a line into polar. But notice, just to write a very simple line, you need trig in polar. So y is r sine theta, m stays right where it is, and then this is r cosine theta. Okay, and we want to get r by itself. So what would be the first step to at least getting r by itself? We want to at least get all the r's where? Yeah?
On the left side.
Yeah, at least get them all on the same side. All right, that's the first step. So you can subtract this term to the other side. So you have r sine theta minus Mr. cosine theta equals b. Okay. Now, what could I do on the left-hand side that would make it so I would only have to write the r one time?
Factor it.
Factor it. Let's factor the r out. What would that leave me with in parentheses?
Sine theta minus m cosine.
M cosine theta. And lastly, how would you get r by itself?
Divide by sine theta minus m cosine theta.
Divide by sine theta minus m cosine theta. And that is the equation of a line in polar, where b is your y-intercept and m is your slope. So let's try it. Let's try an example where our y-intercept is 2 and our slope is a half. So let's type this in, and this will be our first equation that we type in polar. All right, so we turn the calculator on, go to mode, and now you're going to go to polar. Once you go to polar, you're going to see a screen, and it's going to say r equals. Whenever you graph something in polar, you have to get r by itself, just like in function notation, you have to get y by itself. It's got to be a little careful with parentheses as we type this in. So our y-intercept is 2, divided by, in parentheses, sine, and to get the theta button, you're going to press the button that you would use for the variable, which is, well, sometimes it's an x if you use function, it's a t if you use parametric, it's a theta when you use polar. So sine theta minus my slope, 0.5 cosine theta. All right, now order of operations, I think everything should be okay. But I need to go to my window, and I need to make sure that theta goes through all the different values it could get before it repeats. What's the period of the sine or cosine function? 2 pi, or I'm in degrees, so I'm just going to go 0 to 360. That means by going from 0 to 360, theta will take on every possible value that it could before it repeats itself. Now, theta step, go by twos. So 0 to 360, counting by twos, that's 181 points. That's fine. That's a lot of points, and I don't think it's too many, but it's enough that you should get a good sketch. So let's see if we have a line with a slope of 1/2 and y-intercept of 2. Now, you noticed how it sketched it. It kind of like, it went down into the left first, and then it shot back to the right. That usually happens when you graph it in polar. And it has to do with the sine and the cosine changing from a positive to a negative. So if your radius becomes negative, all of a sudden it shoots you over to the other side. Then when it becomes positive, it shoots you back the other way. But there you go. So that's a line in polar. It's got a y-intercept of 2, and the slope up 2 over 4. Yeah, slope is 1/2. So not impossible to do lines in polar, but certainly a lot more complicated equation than y equals mx plus b. You have to understand trig to do it in polar. Any questions on that?
Why does my graph look like this?
Did you set your window and your theta step and parentheses and your equations and all that stuff?
Oh, wait. No.
Okay, yeah, you need parentheses because otherwise order of operations won't be correct. So that's what you type in.
I use the fraction button.
Yeah, there's different ways you can do it. All right, so now we're going to look at another graph in polar, a lot more complicated than just a simple circle or a line. But what I want to do is kind of figure out how to think about what something looks like in polar. So we're going to make a table and figure out what's happening. We're going to break this graph into sections. And if you look at it one section at a time, I think it helps it make sense. So that's what we're going to graph. 3 plus 3 sine theta. And we're going to let theta go from 0 to 360. Or 0 to 2 pi. Now, let's think about what the radius is going to be between. Because this is not a fixed radius graph. Fixed radius is just r equals a number, and you get a circle. What's the biggest value that sine can ever be? 1. And if you multiply that by 3, and add 3. 6. So you're never going to be further away than 6 units from the origin when you sketch this. Now, let's see what the smallest distance we could be is. What's the smallest that sine can ever go? And then multiply by 3.
3.
And then add 3.
0.
0. So you will have a radius of 0, which means this graph is going to go through the origin. All right. So at least it gives us an idea of how far away we are going to be. So here's the graph of sine. Right? And I want to think about this graph in 4 parts. There's an increasing part till you get to pi over 2. Then it's decreasing, and it hits the axis when you get to pi. It continues to decrease, and it bottoms out at 3 pi over 2. And then in the 4th section, it increases till you get to 2 pi. So we're going to kind of look at those 4 sections one at a time and see what effect that has on the radius. And the reason we're looking at the graph of sine is because this equation has sine in it. So we're trying to look at just what's happening here, and then it'll explain what's happening to the radius itself. Any question on that idea? All right. So to make a table, and what we're going to do is in the left column, we're going to write down the sections we're going to look at, and there's going to be 4 of them. We're going to look at the 0 to pi over 2. Then we're going to look at pi over 2 to pi. Then we're going to look at pi to 3 pi over 2. Then we're going to look at 3 pi over 2 to 2 pi. So those are the 4 kind of key sections in the graph where things change.
What's the equation we're looking at?
So the first thing I want to look at is what is happening to the sine function. Not even the function we're going to graph yet, just a small piece of what we're going to graph. So as you go from 0 to pi over 2, what happens to the sine function? It goes from what to what?
0 to 1.
It goes from 0 to 1. If you know that the sine function is increasing from 0 to 1 over this interval, that's going to help you figure out what's happening to this radius. So the sine function is starting at 0 and it's ending at 1 for its range. So if the sine function starts at 0, what's the radius going to start at?
1, 0.
0.
This is starting at 0. So what's my radius starting at? 3. If this is 0, and you triple it, you get 0, and you add 3, you get 3. So our radius in this section is going to start at 3, and it's going to grow. What's my radius going to grow to?
4.
What's the sine function going to grow to as maximum?
6.
Well, the sine function is going to grow to 1. And then 1 times 3 is 3, plus 3 is 6. So on your graph, in the first quadrant, your radius needs to grow from 3 to 6. So it's almost like it's going to spiral out from 3 to 6. Now, let's look at what happens from pi over 2 to pi. What happens to the sine function as you travel from pi over 2 to pi?
1 to 0.
The radius, the sine function is decreasing, starting at 1, ending at 0. So what's going to happen to my radius? It's going to go from 6 back to 3. So in quadrant 2, the graph is going to spiral back in. It's actually going to be symmetrical to what you did in quadrant 1, but decreasing. So it's going to look like a mirror image. All right. Now, what's happening between pi and 3 pi over 2? It's going from 0 to -1. So we're figuring out what the graph is going to look like in quadrant 3 now. What's my radius going to start at in quadrant 3? It's going to start at 3. And as I move through the third quadrant and get basically to the negative y-axis, what is my radius going to be at that point? 0. So it's going to spiral in towards the origin. And now I'm going to travel back through the fourth quadrant. What's happening to the sine function from 3 pi over 2 to 2 pi? It's going from -1 to 0. And what's going to happen to my radius if this starts at -1 and then plug that in?
0.
So we're going to go 0 to 3. So that's also going to be a mirror image of what you did in quadrant 3, spiraling back out. Okay, so now we have to think about what that looks like. Let's try to sketch it. So we've got some definite points. We know that when we plug in an angle of 0, we end up with a radius of 3. That's what we just went through. You plug in an angle of 0, that gives you a sine of 0, which gives you a radius of 3. So what I'm focusing on are these two numbers. Those are like my coordinates. Here's my r, here's my theta. So r is 3, theta is 0. So graph 3, 0. Now, when we end this, at the end of quadrant 1, theta is pi over 2, and that gives me a radius of 6. So graph the point 6 pi over 2. Where's that? 6 pi over 2. Yeah.
It's going to be on the, I don't know how to say it the right way, but what would be the y-axis on the 6 dash?
Yeah. it's just going to be up 6.
Yep.
So up 6. 1, 2, 3, 4, 5, 6. So what's happening is as you travel through the first quadrant, the radius is growing from 3 to 6. So if you want to think about that as having like radial lines, I'm going to erase these lines after, but it's going to be here, and then it's going to grow. And these lines are going to keep growing until you get all the way up to your maximum. So that's the idea of what's happening along the edge of this graph. The radius is constantly growing from 3 to 6. So it would look kind of like that. These are hard to draw, but that's the idea. Now, it's going to be a mirror image as you travel through quadrant 2. It's going to go from 6 back to 3. So the first point you would graph is a radius of 6 and an angle of pi over 2. Well, we already did that, 6 pi over 2. It's going to end at 3 pi. That's 3 comma 180. So it's going to end right there. So it's going to be a mirror image of what it did in quadrant 1, shrinking back. So let's take and copy that and flip it. Okay, so we got that part. Now we have to figure out what happens as we travel through quadrant 3. As you travel through, this was quadrant 1, 2, 3, 4. The radius is going to shrink from 3 to 0. So graph this point, 3 comma 180. Okay, we already have that. And now graph the point 0, 3 pi over 2. Where is the point 0, 3 pi over 2?
The origin.
The origin. So you want to imagine what's happening this time. The radial lines are shrinking. So it starts at 3, and as you pivot towards the negative y-axis, the lines are getting shorter and shorter and shorter until they finally end up right at the origin. So what's happening here is something kind of like that. And then they're growing again in the fourth quadrant, spiraling out from the origin, 0 to 3. So they're going to grow again. So let's clone that and just make a mirror image of it. And there's kind of what it pretty much looks like. Anyone have I'm going to graph it on the calculator, but anybody have a thought what they think it kind of looks like?
Upside down heart.
Eggplant.
Kind of looks like an upside down heart. Like if you take and group all that together and then spin it around, kind of like a heart. Doesn't quite come to as much of a point as a heart, but yeah, it kind of should look like a heart, and that's why this shape is called a cardioid. That's the name of this graph. It has kind of a heart-like shape. In general, cardioids pretty much, if you're drawing a standard cardioid, have the same number here and here. 3 plus 3 sine theta, 5 plus 5 sine theta. This number, if you change it, will control the size of the cardioid. But in general, cardioids, it could be plus or it could be minus, but it's the same number. 2 minus 2 sine theta, that would be a cardioid. And you can also do it with cosine. Now if you remember, sine and cosine are phase shifts of each other. They're 90 degrees apart. What do you think a phase shift of 90 degrees would do to something in polar?
Negative.
It's going to what?
Make it negative.
Flip it.
Not flip it, but think about polar. What happens in polar when you shift 90 degrees?
I rotate
It
it.
rotates it, right? Because we're in polar. If it was a phase shift in function, it would move left and right. But if you graph something as sine versus cosine, you can rotate the heart shape, whichever way you want. And if you make them negatives, that can flip it. things like that. So you can make the heart basically face any way you want. All right, let's just try typing that in. What were the numbers for the cardioid? 3? So 3 plus 3 sine theta. A couple things you want to check. Let's do it in radians. So I need a full cycle. So I want to go 0 to 2 pi. How about my theta step? If I go from 0 to 2 pi by 2's, is that good?
No.
No, that's bad. Because you're only going to get 0, 2, 4, 6. You're going to graph 4 points for this whole thing. Cardioids need way more points. So what would be a good value to go by? 0.1. If you go by 0.1, you're going to graph 10 points per integer, and you're going to end at 6.2. So you're going to have a little gap at the end, but that's not bad. Let's do zoom 5. And you can see it kind of looks like what I drew. Maybe mine should have been a little bit smoother at the top, but again, a cardioid is kind of hard to draw. But that's the idea. That's a cardioid.
Well, it has like a much larger gap. It's like
If it has a larger gap, it's probably because of the.
I have the exact same thing.
And you're in radians?
Yeah.
Okay, that's okay. Like if I did 0.5, I would get a much larger graph, and it doesn't look as good because I didn't do enough points. All right, so you want to make sure cardioid should look like a curve, not like a polygon. The only thing you can't let A be is 0, because if A is 0, then you just wiped everything out. So you can't do that. But A can be anything other than 0. And you can play with it. These aren't cardioids, but if you change these numbers, like let's let one of them be 3 and let one of them be 4, you start to get different shapes. Right, so if we did like, let me fix my theta step first. Let's make this one a 5, and let's keep the other one a 3. So what happened there is it kind of reduced the amount of the heart shape, the amount that it kind of went in on itself on the graph. It changed it. Now, if you do it the other way, make the number next to sine bigger, you're going to get a graph that loops back over itself. So not technically a cardioid, but it has kind of a little bit similar look. And if changing sine to cosine, we can just do that real quick. Instead of it looping at the bottom, it's going to loop, and it's now facing like the right. All right, so any questions on those? Those are cardioids. Well, that's not, but the other one was. Okay, so let's take a look at how we can take something that's polar and change it to rectangular. By doing this, I'm not saying you're going to be able to plug it in on the calculator, because you may end up with so many y's in your equation that you can't get y alone. Right? For example, cardioid would be a very difficult one to graph as a function, because think about it. If you draw a vertical line, does it pass the vertical line test? No. So you're not going to be able to type this in. You can change it to a rectangular equation, but it's not going to be something you can type in on the calculator unless you split it into multiple pieces and maybe draw like a top part and a bottom part, kind of like a circle. But think about all the different formulas that we have. Okay? These are all different formulas that give you some type of connection between function notation and polar. Right? This gives you a way to turn an r and a sine into a y, a cosine and an r into an x, and so on. But the goal, when you write something as a function, you have to have x's and y's. No r's, no thetas, no sines, no cosines. You just want x's and y's. So let's take the equation for a cardioid and let's convert it to rectangular. See how to do that. So several things here I don't want. This is bad. That's bad. Can't have those two things. Let's start with the r. Preferably, if I can substitute something for r and not get something else that I have to substitute for later, that would be good. So I would like to change r to something that could be my final answer. Does anybody see something that r equals and it only has x's and y's in it? Like, yes, you could say x divided by cosine equals r, but then you got to fix cosine. So I'd rather not do that. Yep.
X squared is y squared.
I could substitute x squared plus y squared for r.
No,
Just x plus y.
no.
Or no.
The square root of x squared plus y squared.
Yes, r is the square root of x squared plus y squared, which is not x plus y. Okay, so just be careful with that. So r is the square root of x squared plus y squared. So we got rid of the r. And that equals 3 plus 3. Now we have to get rid of sine theta. Well, you don't have much of a choice about what formula you're going to use to do that. What is sine theta equal to?
Y bar.
Y divided by r. So we can get rid of the sine theta. But now we have one more thing we have to get rid of, which is that r. So we already know what r equals. I think what I'm going to do here, I want to clean that up before we get rid of that r. I don't really want to have a fraction like that. So let's think of it like this. What could we multiply everything by that would get rid of that fraction? Pi. So it actually might have even been better to do that before we change this, but that's fine. So let's multiply everything by r. So we get r times the square root of x squared plus y squared equals 3r plus 3y. And now, what did we say r was equal to?
Square root of x.
Square root of x squared plus y squared.
Yeah, and if we had just left this as r and didn't change it, we would have just multiplied it by r. So technically, this is now r squared on the left, because it's r, and we had r before. So the left-hand side just becomes x squared plus y squared, because the left-hand side is now r squared. And r, you guys just told me what that was, the square root of x squared plus y squared plus 3y. Are there any r's, thetas, sines, or cosines left in that? Okay, no. So that's it. That's the equation of a cardioid in function notation. Now, you're not going to be able to graph that and get y by itself, because you have y in too many spots. It's not going to easily be solvable to get y alone. But that's not what they wanted. They just wanted you to change from polar to function. Any question on that? So keep in mind those 4 formulas. Those are generally what you use to do it. We only use 2 of them this time. No, we use 3 of them. We use 3 out of 4. Okay, now we're going to look at how we can change something from polar to parametric. All right. So let's say that we have some graph in polar. It doesn't matter what it looks like. You got some kind of graph in polar. In polar, think about what you know about something in polar. The 2 things that, what are the 2 things that you're always given for a single point? You're given a what and a what? Yep. You're given a radius and an angle. Well, here's your radius. Now, is that radius the same for every point on this graph? No. It might be the same for couple of them depending on where you draw it. But in general, no, the radius is a variable. It changes. How would you figure out the radius? Well, that's where they have to give you a formula. They'll give you a formula that says r equals. So you will have an equation to draw this picture. So you can figure out the radius at any point just by plugging in something. What's the other thing that they give you when you have a point in polar?
Angle.
They give you the angle. This right here that is your angle for that particular point. That's the angle, and that's the radius. So the radius and the angle are the only two things you need to figure out how to write this in polar. Because think about making a triangle to that one point, and then imagine doing it to every single point. So it would be different triangles for every point. There's your x. There's your y for this particular point right there. How would you get, or what trig function would you use to get the x value?
Tangent.
Which one?
Tangent.
Tangent? No, because you wouldn't, if you're trying to get the x value, you're going to know this, and you're going to know this, and you're trying to find this. You would use cosine. Right? Cosine of theta equals, and what side is adjacent? X. Now, you can't put r in the bottom because r is not a fixed value. R changes depending on what point you're drawing a radius to. So what would you put there? This is a formula. The formula is going to be some function in terms of theta. In the problem we're going to do, it's going to be 7 sine 2 theta. But you've got to use a formula in the bottom to find the radius because it's different at every point.
So that's the equation you change from polar to parametric.
And now we got to get x by itself. So x would equal some function in terms of theta that's going to calculate your radius times the cosine. And then what would y equal? Like,
Would it be that same thing except for cosine and sine?
yeah. So we've done this kind of thing before. The only thing that was different, we did it on a circle and the radius was fixed. So you had a number. Now you have a formula for the radius because you don't know how big the radius is going to be. It's different to every point. So you have to calculate the radius every time using your formula. Now, the only thing we have to remember when we write this in parametric, what variable do we use? We don't use theta. We use what?
T.
T. So, when writing parametrically, use T in place of theta. That's just a notation thing. We don't use theta. So it's going to become f of t cosine t, f of t sine t. So it's always the formula they give you for the radius. So this part right here is like your radius times the cosine, and then your radius times the sine. It's just a constantly changing radius because it's not necessarily a circle. It could be anything. So let's try this one. Here's our problem. This is the formula to calculate the radius. So that's what you start with. Just make sure you change the theta to a t. So what's the formula to calculate my radius when I write it in my final answer? Just the radius, yep.
Would be 7 sine 2 theta. Or
Well, what do
t.
we change theta to?
T.
T. So this is the radius. But what do you always multiply the radius by to get the horizontal? Yeah? Cosine. Yeah. This is your radius times the cosine. And this gives you your horizontal. This is your x. Now what about your formula for y? What's your radius? Oh, Tim?
7 sine 2t.
So your radius is 7 sine 2t. So that's calculating the distance from here out to a point. Now I specifically want this. I want the y value of that. So what do I multiply the radius by to make it the y value? Sine t. So you're either multiplying the radius by cosine or the radius by sine. And that's it. Let's try. So let's graph 7 sine 2 theta in polar. So 7 sine 2 theta. Check your window real quick. Looks fine. Graph. Okay, and that's the shape you get when you do 7 sine 2 theta. Now, so this is polar. Let's switch over to parametric, type that in, and see if we get the same sketch. So go to mode, put it in parametric, and you're going to do your radius times cosine, and then you're going to do your radius times sine. Right, check your window. 0 to 360. Nope, that's not going to work. I only want to go 0 to 2 pi because I'm in radians. And I don't want to go by 2s. What would be a good step? 0.1. Let's hit graph. And it drew it. I think it drew it a little bit slower than the polar one. So maybe that means polar is a little more efficient, if you want to use that. But that's how you can convert something from polar to parametric. Now, look at the equation. Look at that 7. That 7 is in the picture. Does anybody see what the 7 is in the picture? Or what it's controlling? That might be a way to say it. Let me draw something that's 7 units long. So 1, 2, 3, 4, 5, 6, 7.
Is it the radius?
Is it like the maximum radius?
Yeah. If I take this and rotate it, or I can move that, and put it, it's not perfect, but you probably get the idea, right about there. That 7 is the maximum radius that you ever get. And it's the length of the petal. So the number in front controls how long these petals are. That's what they're called, they're petals. What about this 2? That's a little tricky. Anyone think they know what the 2 is doing? Okay, I guess it could partly be controlling the width because of what I'm thinking it also does. Yeah?
Is it where they like intersect?
They're all going to be right at the origin.
Oh.
Yeah, you could shift it in parametric if we wanted, but we're not going to be shifting it. Well, let's try 4. So instead of, let me go back to polar, because that one was easier because it's only a single equation to change. Let's make it a 4 theta instead of a 2 theta.
The amount of petals in each quadrant.
So what do you think the connection is between theta and the number of petals? The number in front of theta.
Each side.
It's doubled.
It's doubled those, right? When you had a 2, you got 4. When you had a 4, you got 8. Maybe we need a little more detail here because these edges are starting to look a little kind of jagged. So probably want to decrease your t-step a little bit because you have more curves going on. So it looks like if you put in a number, let's try like 6. How many petals do you think we'll get? 12? Yeah, we definitely need to decrease the t-step. And if you count that out, you should have 12 petals there, but they should look smoother than that. So what if I put in 5? How many should I get? Got 5. So it's a different pattern if it's even or odd. If it's even, you get double the number of petals. If it's odd, you get exactly that number. So I'll leave it to you to figure out how you could get like 6 petals. You couldn't type in 6 because you'd get 12. If you type in 2, you get 4. If you type in 5, you get 5. 7, you get 7. How could you get 6? No, there's a way to do it. And whether you change this to sine or cosine, that's going to control the rotation. The difference between sine and cosine is a 90-degree rotation. So now all your petals are going to be centered on the axes because I changed from sine to cosine. So you can see how they were before and how they are now. So anything of the form r equals a sine 2 theta, okay, they call that a 4-petal rose because it has 4 petals. And the length of the petal is the absolute value of the number in front because length can never be negative. You could try putting a negative in and see what that does. See what how the graph changes. Any question on that shape? All right. So the last shape is a spiral. So the idea of a spiral is it's kind of like a circle, but the radius is constantly growing. It's always growing, or shrink, depending on which way you're spiraling. And this particular spiral is called the spiral of Archimedes, and it's where the radius is exactly the same size as the angle. So if you're at an angle of 90, your radius at that point is 90. If you're at an angle of 120, your radius at that point is 120. So the bigger you make the angle, the bigger the spiral gets. Like,
I got 6 petals.
you got 6?
Yeah.
Oh, good. I'll take a look at it, see how you did it. So let's graph r equals theta. Now it's a spiral, so is there really a point where you could end and see the entire spiral?
What if you have T min and max?
Well, yes, with a T min and max, it'll limit it. But I mean, like with a circle, you're going to get to a point, I don't care how much bigger you make the T max, you're never going to see more picture because it's a circle. Is there a point where you would never see more spiral if you keep increasing T max? No. So when you're drawing a spiral, I would say 2 revolutions of the spiral is probably enough. So what would I have to go to see 2 revolutions? Yep.
4 pi.
4 pi. Now, think about your min and max a little bit. There's only one place in the spiral where it's actually going to hit 4 pi if you go around 2 times. That's 2. No, that's 1. That's 2. What part of my graph, the x min, x max, y min, or y max, needs to be the biggest?
The X max.
The x max, that is the only place that you're going to hit that's where you will hit the maximum radius of your spiral. I'm gonna set everything to the same, x min and x max, so it's a little overkill, but I know that if I'm going 0 to 4 pi, the biggest my spiral will ever be is 12.5 units from the center. And that's only gonna happen on the x max. But let's set them all to 12.5. So theta step, I think 0.1 is probably okay for 2 revolutions of a spiral. So let's go negative 12 and a half, 12 and a half, negative 12 and a half, and 12 and a half. Oops, and type your equation in. So R equals theta. And you can see the only place that I hit the maximum was at x max. So if I did, I'm not going to go through them all, so I just did 0 to 4 pi. What would happen if I did 0 to 2 pi for my T min, T max?
Be smaller.
It would
Yeah,
just be one.
I just get 1 revolution. And what if I did 0 to 8 pi?
You'd get more.
Yeah, I get how many revolutions of the spiral would you get from 0 to 8 pi?
Two.
How many, Nick?
2.
We got 2 right here. This is 2. Now it's 0 to 4 pi. 4. Yeah. Yeah, you get 4 spirals. How many?
4.
Yeah. So you get 4. And you can try, like, you know, I don't know, try instead of 0 to 12 and a half, go negative 12 and a half to 12 and see what that does. Or negative 12 and a half to 0. Let's do it that way. Let's see if you can see what's different about it. So first of all, it's different the way it drew it. It spiraled from the outside in. And it looks like it's a mirror image. If you look at it, it's also been reflected horizontally. So depending on how you change your parameter, you can mirror image the spiral, and you can make it spiral different ways. Play with it, see if you can make it go clockwise versus counterclockwise. Draw it a different way. Right? All kinds of different things you can do. Right? But that's called the spiral of Archimedes.
How do we use that? Like, what does that do for us?
What does it do for you?
Yeah.
It'll enable you to answer a question on the test.
Okay. Is it used in calculus at all?
So a mathematical application of a spiral?
Yes.
Uh,
That's what I was getting at. I didn't even know what you knew about that.
I'm not sure about spirals in calculus. I wish Mr. Babb was here. Honestly, I'm not 100% sure.
Can we come back to help?
Tomorrow?
During period 4.
Oh, wow. Well,
During period 4. Yeah, like 10, probably 10, 15. So the last 20 minutes, yeah.
Are you gonna like double check those like you normally do?
Am I gonna double check it? I think it's okay.
Okay.
Yeah,
Sure.
I'm pretty sure. Yeah.
How long should it take us?
How long should it take you? I don't know. Let me take a look at it.